Alright, let's take a look at the non-standard conditions. As you may recall from our thermodynamics lecture, I did mention at the end that when the conditions are not at equilibrium, you're dealing with non-standard conditions, in which case you deal with delta G without a naught, but that is equal to delta G naught plus the RT of ln of Q, where Q is the reaction quotient that you compare to the equilibrium constant to see whether you shift to the product side or the reactant side. Alright, so because delta G has an electropotential value associated with it, we have delta G without the naught being equal to negative NFE without the naught, and that equals negative NFE with the naught plus RT of ln of Q. So if you divide negative NF from both sides of the equation, you're going to end up with E without the naught equals E naught minus RT over NF ln of Q. And applying the same change that I showed you before, and assuming that the temperature is 298 Kelvin, ultimately you can change all of the constants in front of the ln of Q and change the ln of Q to log of Q and end up with 0.0592 divided by N times the log of Q. And this whole equation here is what we call the Nernst equation. And it allows us to look at the potential of redox reactions when you haven't yet achieved equilibrium. So let's take a look at one of those processes. So this kind of takes us back a little while back, like the beginning of the course, where we were looking at this equilibrium H2 plus I2 turning into 2HI. At the time, you might have not acknowledged this, but if you look carefully, you realize this is actually a redox process because hydrogen starts with a charge of 0. Same thing for iodine, but by the time you get to the products, hydrogen has a +1 charge and iodine has a -1 charge. So technically, this is a redox process. So you could ask the question, if the initial concentrations are 2 times 10 to negative 3 molar, and for iodine and HI, the concentrations are 10 to negative 3 molar, knowing that the equilibrium constant is 51, what are the concentrations at equilibrium, right? You could ask all of that to find the equilibrium constants, which means that you'll have to use a nice table to figure all of this out. But before you can do that, you had to apply and determine the value of Q to know whether you were shifting to the right side or the left side of the equation. Alright, so let's take a look at this. You start with H2 and I2. These two particular reagents don't overlap with each other. So they're going to react to give you ultimately H plus and I minus. And your Q is given by HI to the second power divided by H2 divided by I2. And so when you input the values, you find out that your Q ends up equaling 0.5 in this specific example. Compared to the value of K, this will tell you that K is greater than Q, meaning that this is going to have to shift to the product side. But let's see what happens when we apply this to the electrode potential. The potential of this process, since the reduction of iodine is 0.53 and the oxidation is going to be positive 0.0, you end up with a cell potential of 0.53. Inputting this into the Nerst equation and accounting for the fact that going from H2 to 2H's, you're actually using 2 electrons. The value of N is 2. Multiply 0.0592 divided by 2 by the log of 0.5. You're going to find out that that equals 0.0089, which then gets subtracted in this case, since this whole thing ends up being negative, from 0.53. And so E is equal to 0.52 volts. And the fact that E without the naught is positive tells you that the reaction is spontaneous as written. In other words, you will shift to the product side and you will make products. And this is exactly what we got by applying Le Chatelier's principle, or looking and comparing the value of K to Q. So this is just another way to approach the same problem. Alright, now let's take a look a little bit further. Let's take a look at KSPs and see how we can apply the process. Now, you might remember that for silver and iodide, you form your insoluble solids. There's one specific thing about it that is kind of interesting and rather bizarre, if you actually look at the reduction potentials for silver and iodide, you're going to find out something rather unique. First of all, silver plus and iodide don't actually overlap with each other, and yet you can make silver iodide solids, which coexist with each other. They're literally in the same unit cell. So how the heck is it possible that silver plus and iodide don't react with each other to give you silver metal and iodine when you have them present in the same ionic complex? Why does this not happen? Well, to address this question, right, the fact that we're not seeing the reduction of silver and the oxidation of iodine in the balance equation here, we have to ask ourselves the following question. If this is something we can make and store, then it's going to be stable, at least to some extent. So what is making this behave as a stable species when the reduction potential tells us otherwise? Well, if you think about the insoluble salt, silver iodide, we have a KSP value for this, right? We have silver plus and iodide minus as the soluble species based on the KSP. And if we apply the KSP equation, we'll find out that KSP equals x squared, which means that the solubility is going to be 9.23 times 10 to the negative 9 molar for both silver and iodide. Okay, so what this basically tells you is that if you were to add the solid to water, at most, you will have 9.23 times 10 to the negative 9 molar of silver plus or iodide, and that will be the only concentration you're going to have. So, thinking about the Nernst equation, we know that for silver going to silver 0, the reduction potential is 0.8. We are dealing with 2 electrons in the process. We divide 0.0592 by 2. And then for silver, since silver plus is the reactant, that's what goes on the denominator of your equation. And notice that right here I'm only applying this to just silver, but you could also include iodide, and then in that case you'll have to use the E cell of the entire reaction as opposed to just silver. But I want to show you something interesting here. I'm kind of separating them now for the time being, but so this is silver and then this is iodine, and iodide is the product, so it's on top, being raised to the second power, right? When you input the actual concentrations of these two species, you're going to find out the following. For silver, the value of the potential non-standard ends up being lower to 0.32, and the value of the potential non-standard for iodide ends up being raised to 1.01. So the fact that the concentrations are pretty low in solution to begin with means that our diagram in reality, it looks more like this. The value gets dropped to 0.32 for the reduction of silver, and the value for the iodide oxidation gets raised to 1.01. So in fact, silver and iodide under these non-standard conditions actually do overlap with each other. And this is the reason why they're actually stable. So the moral of the story is that when you look at the traditional reduction diagrams, you have to keep in mind that they are based on the idea that everything is under standard conditions. And standard conditions means that you have 1 molar concentration of all the species present, which in most cases will not be the case. Alright, so this is one way to explaining some of the things that we're going to be seeing, and it's also one of the ways by which you're going to be able to see whether, keeping the concentration of a reagent that ought to be reactive towards another can make the difference as to whether they're stable towards each other in the presence of each other, just by lowering that concentration. Alright, so in the next video I'm going to show you what happens when you start changing the pH.